Welcome back. This is page 19 of part 2 of Laplace transform. In the next few slides, we'll go through how to perform Laplace transform on some functions. The first functions that we'll deal with is the unit step u of t, or the Heaviside functions. Now, for this unit step, it is 1 from time 0. So this is time, and the value is 1, and 0 before time 0. Since this is a causal signal, when we perform Laplace transform, we can use the unilateral transform. So the lower index is time 0, and the upper index is infinity. The unit step ut e minus st. Now, since ut has value 1, this basically reduces to this. That means ut seems value 1. We are back to integral of 0 to infinity e minus st dt. Please remember your integration methods. The integral of ekx dx is equals to 1 over k ekx. So in this particular case, s is the variable that we can move down here. So this is minus s. We have the e minus st, the function, and t goes from 0 to infinity. We substitute into this. When t goes to infinity, e minus st goes to 0. So minus 1 and minus 1 cancels, become plus 1. The answer is 1 over s, is the Laplace transform of the unit step. Again, remember that for this value to go to 0 as t goes to infinity, s must be greater than 0. Only then would this limit goes to 0. So this is the region of convergence. This is the Laplace transform of the unit step, and we have this additional entry in the table. Let's proceed to the next function. In the next function, we are going to perform the Laplace transform of cosine bt. Now, recall that the Laplace transform of exponential minus at is 1 over s plus a. The cosine bt can be represented in this form by remembering the Euler's formula. Remember, ejbt is equals to cosine bt plus j sine bt. E minus jbt is equals to cosine bt minus j sine bt. When we add both of them together, we have 2 cosine bt. Here we have plus 0 because the imaginary terms cancel, and therefore now we have this expression e plus jbt plus e minus jbt divided by 2 is equals to cosine bt. Right. Also remember that Laplace transform is a linear transform. It means that we can deal with each of these individually. We can do this, Laplace transform of this, and plus Laplace transform of this. We bring the half out. So Laplace transform of cosine bt is half, bracket, and then we perform the individual Laplace transform of e plus jbt and e minus jbt individually. Well, Laplace transform of ejbt is of course 1 over s minus jb. We're just using the lookup table. Laplace transform of e minus jbt is this. So the minus becomes a plus here, and the half goes out. Alright, so all we are now having is this complicated expression, which we are now going to form into rational functions. So basically, this goes on top, this goes to the other side, and the denominator becomes a multiplication. So we have s plus jb, s minus jb, and then we'll work out the sum. This is the final solution, which is s divided by s squared plus b squared. I'll leave the sign for you to do it by yourself. This is the same process. Right. So now we're going to do the next one, which is Laplace transform of, see, we have cosine, but we now have e minus at multiplying by the cosine bt. This looks like a more complicated function, but let's interpret this. First, we have a cosine that is going on. I forget to tell you that we are using unilateral transform, so actually I should have ut here. But if I've not mentioned this, you can assume that the signals of our interest is causal signal. What about this guy? This e minus at is a exponential decaying. If a is positive, then the decaying will go down and become 0 as time goes to infinity. Right. How do we perform this? I think the trick again is, well, let's express the cosine as sum of complex exponential. So we have e minus at here. We convert the cosine into this as before in our previous example. What we do is that we distribute e minus at with the terms inside this bracket, and we get this e minus, then the whole thing is a minus jb. Now why minus jb? Is because this minus and this minus will become plus. So what happened is that it will basically generate the first term, this guy multiplied by this guy. Over the second term is e minus at multiplied by e minus jp. So we have a minus and we have another minus. So if we bring the minus out, the inside operator, it becomes plus. It's e minus bracket a plus jb t. Now, then we apply the same trick, really. And remember, the trick was that we have Laplace transform of e minus at equals to 1 over s plus a. So this a here is now the entire expression a minus jb. So we have a minus jb as the first term. We have a plus jb as the second term. And because this is minus, this becomes plus. Again, we apply linearity of the Laplace transform, and we have done this to time domain signals separately. Alright, you go through the algebra, and basically again you're putting this term on top, you're putting this term to the other side, and you're multiplying the bottom terms together. So you have the expression below, and you open it up, you can get this. And in the top, if you do the computation correctly, you get s plus a. So this is the answer. The Laplace transform of e minus at cosine bt is equals to this expression over here. Now, observe this. We have cosine bt. We have cosine bt. The only thing we add is this guy, e minus at. And look at what changes in the Laplace domain. S plus a. So the s is replaced by s plus a when we multiply the cosine by e minus at. So that is the property which you'll learn later on. All right. So we have done 3 examples of Laplace transform. In the last example, the function of is t, I should write ut for causal signal. Again, remember, if I did not tell you, we can assume that we are only dealing with the unilateral Laplace transform. Right, so let us write the Laplace transform, and then we get this expression here. It is the integration of from 0 to infinity the function f of t e minus st dt. So when you look at this complicated function, what can we do? Well, I'm going to advise you to do integration by parts. And in the integration by parts, you will have your choice of u and dv. I'm going to tell you that the correct choice of u is t, du is 1, dv is e minus st, and then of course v will become integration of e minus st dt, which is e minus st over minus s. Now if you carry out the integration by parts and solve, you'll get the answer. I'm not going to go through, but I'm going to show you where you can find this in YouTube. Google Laplace transform calculating the Laplace transform. The complete name is by this person called Patrick JMT. He did this about 11 years ago in 2011, and this video has already have 394,000 views. Now, where is I'm going to now play a section of it here.
The integration by parts formula, infinity, because that's the original upper limit of integration. And then we have to integrate this t e to the negative st dt.
Right. So from about 2 minutes 42 seconds onwards, he did this question, which is what we are trying to solve. So you can look at this video and you'll be able to find details of how he solved. But again, he also did like what I have done, which is integration by parts using u equals to t and dv equals to e minus st. Right. If you have done all the computation, the end results will be this. The Laplace transform of t is 1 over s squared. With the ROC, the real part of s must be greater than 0. And with that, we are done with examples of Laplace transform, the forward Laplace transform. Thank you.